Okay, so now so let's see a problem. Here we have a problem where it states that select a grade S355 UKC section for NED 1000 kilonewton with LE 9 meters. So now NED is the design effect. So N stands for axial load. So there is the axial load of 1000 kilonewton acting on a channel section. So S355 channel section, and it has an effective length of 9 meters. So we need to look at the we need to choose an appropriate section that can handle this load. Okay, so if we start that, I have covered this one earlier also. Now there are two states, two limit states we have seen. One is ultimate limit state, other one is service limit state. So under serviceability limit state, we have to see whether the structure can satisfy serviceability limit state requirements. One of that requirement is deflection, and another requirement is vibration, and there are requirements on the crack length as well, or crack width as well. So service limit state loads occur more than once during the entire service life of structure, and steel must remain elastic during the service limit state loads. An elastic deformation should satisfy the requirements given by here. So for uh, a beam which is carrying a uniformly distributed load of W, this is the deflection. So this is another example how the deflections are estimated, and any beam or structure should satisfy that deflection requirements. Now if you look at the service limit state requirements in the code does not specify anything explicitly about the deflection requirement. However, the national annexes have recommended some deflection requirements. So for example, the UK's national annex states that, say, for a vertical deflection, if it is a cantilever section, the deflection should not exceed length over 180. If it is a beam carrying plaster or other brittle finishes, the deflection should not exceed span over 360. For other beams, it is span over 200. And purlins and sheeting rails, we need to decide according to the requirement. So that is the recommendations in the national annex of the UK version of this Euro code. And if it is horizontal, this is a vertical deflection. Horizontal deflection, normally it's height over 300. So the horizontal deflection, tops of columns in single story buildings except portal frames, the deflection or the horizontal deflection should not exceed height over 300. And for a multi-story building in each story, for each story it's height of the story over 300. So you can add all that to estimate the total allowable deflection horizontally. So those are the service limit state requirements given by the code in the national annex for UK. Similarly, when we have our own national annex, there may be stipulations on these requirements. At the moment, we can take this, or we can use this as the guidance for our service limit state requirements. If you consider the ultimate limit state for a compression member, say if you take a compression members. So if a member which is say you have a member like that supported and then you have a load N. So this due to this load, axial load, you can have squashing of the steel, that is complete failure of the steel by yielding of the steel. Then you can have local buckling or crunching, that is we have seen earlier that there can be local buckling, say a flange may deform in a small area, or you can experience some little deformation on the web, so that's called local buckling, or it can have global buckling. So this can also happen. So there are three possible failure modes when it comes to steel. So under compression, three failure modes. Three, three, three possible failure modes. One is squashing. Second one is local buckling. Third one is global buckling. These are the three possible failure modes. So we need to, when we design a member under compression, we need to consider all these three, and the lowest of these three will be the failure load of your structure. Okay, so or the member. So the lowest of these three is going to be the failure load of uh, the element. So now we are going to look at those in detail. So now if you take a member under compression, we'll take the code, we'll go to the code, 62, take the code, zero code. Okay. So uniform members in compression. So when they are in compression, your NED should be less than or equal to NED over NBRD should be less than or equal to 1. Okay. So this is for the buckling resistance under compression. So then if you look at the 6.2.4. So the first criteria is NED should be less than or equal to NCRD. So NED should be less than or equal to NCRD, and then you have NCRD can be derived from these two equations for class 1, 2, 3. The equation given here is 6.10, class 4, 6.11. So the first type of failure, you have squashing. Failure. So if squashing failure is occurring, your NED should be less than or equal to NCRD. So NCRD obtained from this equation, that is A into Fi over gamma M naught for class 1, 2, 3. A effective Fi into gamma M naught for class 4. So that is A into Fi over gamma m naught classes 1, 2, 3, and NCRD is A effective into Fy gamma m naught for class. So these are the first check. If the failure is occurring due to squashing of the material, then this will occur first. So now if you take our example, that is so here we have an example. We have to select. So NED is 1000, LE 9 meter. We need to choose UKC S355. So NED 1000. Okay. So now 1000 kilonewton should be less than or equal to NCRD. And if we assume that the proposed section is either class 1, 2, or 3, then 1000 should be less than or equal to A into Fy or gamma m. Gamma m naught is 1. Fy is 355 if the thickness of the plate is less than 16 millimeter. So if we substitute them, 1000 into 10 to the 3 in Newton, less than or equal to A into Fy is 355 over gamma m naught is 1. So now we need to obtain the value for A. So A should be greater than or equal to 1000 into 10 to the 3. So 1000 into the 3 divided by 355. So that is 2816.9. millimeter square. So area should be greater than or equal to 2816 millimeter square. So now if we choose this section from the advanced section table, so if I choose this advanced so you can have PDF, or you can you don't have access to this internet when you are this is something else. So So UKC, universal columns. Okay, so these are members which are under compression. So what we need is a section that has a gay area of 2816.9. So that is 2817. So 2817. We have to look at the area. So 2817 millimeter square is like 28.17 millimeter square. So the area is from 16, it is increasing. This is 29.3 greater than 27, 28.17. Here we have another one is 34. Here we have another one, 29.2. So let's take this 29.2, 152, 152, 23, which means it has a dimension of 152 millimeter, 0.4, 152.2, and then 23 is the weight. So we'll take 152 23 UKC for the column. So then the area is 29.2. So that is 29.2 centimeters square, that is 2920 millimeters square. So this is greater than 2816.9 millimeters square. So it satisfies the area requirement. Then we have to see whether it's falling under class 1, 2 or 3. So you have to get CF over TF, CW over TW. So if you look at here we have the ratios for local buckling given here in the table. So I'm not going to calculate again, you know how to calculate. So that is TF over, first one is TF or CF over TF, second one CW over TW. So this first one is for the flange, this is for the web. So CF TF is flange 9.65, web is 21.3. So we need to see whether this satisfies the requirement. And what is the thickness of the flange and the web. So thickness of the web and flange is given here as 5.8 and 6.8 millimeter, which is less than 16, which means you can consider Fy of 355. So since TF and TW are less than 16 millimeter, Fy is 355 Newton per millimeter squared. So now if you get the code, go to the previous section 5.21. For the web it should be CW over TW less than 72 epsilon. Okay, so it's epsilon. This is for bending. For compression, this is the value. So If the member is under bending, this value. If the member is under compression, this is the value that you have to consider, 33 epsilon. So for compression members, CW over TW less than or equal to 33 epsilon means it is class 1. And if it is less than or equal to 38 epsilon means class 2. So now we need to see whether it satisfies class 1. So epsilon is, for 355 steel, epsilon is 0.81. Okay, 0.81. Epsilon is 0.81, and your CW over TW, and your, before we do that, 33 epsilon is how much? 33 into 0.81. That is 33 into 0.81, 26.73. So 26.73 is 33 epsilon. So if our C WTW less than that, then it is class 1. So CW over TW is 21.3. 21.3 less than or equal to 26.73, and then web is class 1. Then we have to look at flange. So in the table again, this is for flange, part subject to compression, part subject to bending and compression. So in this case, the entire part of the flange is subject to compression. So the part subject to compression, so it should be 9 epsilon for class 1. So excuse me, CF over TF less than or equal to 9 epsilon for class 1. So 9 epsilon is 9 into 0.81. So that is 9 into 0.81 is 7.29. So, and our CF over TF is 9.65. That is not equal to 9 epsilon. Okay, so that is not equal to 9 epsilon. So next is 10 epsilon. 10 epsilon. So 10 epsilon also 8.1. So our one is 9.65. So class 2 doesn't satisfy. Then if we take class 3, CF over TF, class 3. So what is 14 epsilon? Is 14 into 0.81. So 14 into 0.81 is 11.34. So 11.34. So CF or TF, that is 9.65 less than 14 epsilon greater than less than, this is less less than 14 epsilon and greater than 9 epsilon. or 10 absorb. Hence, flange is class 3. Therefore, the overall class is 3. So overall class of the UKC is class 3. So that is the classification of the column. And if you look at the data that we have uh, assumed class 1 or 1, 2 or 3, and we took the equation and we picked a section and we checked whether the class is falling under 1, 2 or 3. So now this section satisfies for compression. If the failure is dominated by squashing, so if the lowest of these three load, if the lowest of these three load is equal to the squashing of the material, then this is going to be uh, the section that satisfies the compression requirement. But you can't just expect squashing failure only. Okay, so you have to expect more than that. So the another type of failure that could occur for a compression member is buckling failure. So occur for column is buckling. Okay, so how to determine the buckling load and see whether our section can withstand the buckling load. Okay, so now we have already chosen a section. So now we need to see whether this section can withstand the buckling load or the buckling load is lower than the capacity. So that we have to do. Okay, so now if you take this and go to the code, not the code, it's code. So we can see that buckling resistance only. So when they are under compression, you can have local buckling, you can have squashing. That is what we have seen now. We assume that squashing failure occurs. Then we have chosen appropriate section that can withstand the squashing load. So the next part is compression buckling. So when you compress a column, it tend to buckle. You can try this with the big ruler. If you keep on increasing the load at the end, then what happens is the ruler buckles. So if that type of buckling could occur, okay, so that type of buckling could occur in the member. So now you need to look at how to determine the buckling capacity. So the second major investigation is NED should be less than or equal to NBR. So for buckling resistance, NED so NBRD, NED should be less than or equal to NBRD. And NBRD stands for design buckling resistance of the compression member. Design buckling resistance of the compression member. So now we need to look at how to estimate this NBRD, because we need to make sure that NBRD is greater than NED. Okay, so NBRD is obtained from here. So NBRD is she into, so that is the notation, she into A into Fi over gamma M1. That is for class 1, 2, 3. Then you have another option, that is NBRD, is she A effective into Fi over gamma MD. So that is for class 4, because there's a reduced area A effective into Fi. So, so this gamma M1, gamma M1, gamma M1. So that is class 4 cross section. Now we got already A, we got Fi, gamma M1 is 1. So we need to determine she value. For the section chosen earlier, A is equal to area, gross area is equal to the area we have chosen, that is 2920 millimeters squared. Then A is there, Fy is 355, gamma M1 1. So we need to have the she value. So NBRD greater than NED. So NED is 1000. So NBRD. So NBRD is she into A Fy over gamma M1. So A is there, Fy is there, gamma M1 is there, and we don't know what is she. So if you look at okay, so so your she value should be greater than or equal to 0.964. If the she value is less than 0.964, means your buckling resistance is lower than your squashing resistance. So your she value should be greater than 0.964. If this clause is not satisfied, we need to choose a different section. Okay, so now let's go and see whether this can satisfy this requirement. So 0.964, and if you look at the code, we can obtain the she value from this and the psi from this equation, lambda bar from this equation. But Another option is that you determine the lambda bar. So this is our section is so we'll see the lambda bar. So the lambda bar is given by A into Fi over NCR. So the lambda bar is A into Fi over NCR, square root of that. So now we need to determine the NCR value to determine the lambda bar. So Fy is 355, A is 2,920 millimeters squared. This is Newton per millimeter squared. Then NCR. What is NCR? NCR is critical buckling load obtained from the critical buckling equation. So if you recall the learning in the past, you can remember, or you would have studied that how to estimate this critical buckling load. So if I show you some critical buckling loads, so critical, you can remember this when if I show you, you will remember this. Euler's, that is going to a research article, but anyway, the equation is there. So this is the critical buckling load, NCR or PCR, that is pi squared EI over L squared. You might remember that, pi squared EI over L squared. So NCR is pi squared EI over L squared, and L is LE. So NCR, if you estimate pi squared, E is 200 gigapascal, we can consider into 10 to the 9 gigapascal, Newton millimeter squared, into I value over LE is 9,000 squared. So 9,000 is given in the problem. So now your I value can be obtained from the table. So for this section, I value you can obtain from the next page. So second moment of area, there are two I values. So when you compress a member, it will buckle by the weakest axis. It will not buckle by the strongest axis. So if you look at the I value for this section, 150 to 123, 1250 into 10 to the 3 for strong axis, 400 in the weak axis. So it will buckle by the weak axis, so that is 400, that the value is 400 centimeter to the 4. So 400 into 10 to the 4. So 400 into 10 to the 4. Why 400 into 10 to the 4? Because 400 into centimeter to the power 4 centimeter. When you convert millimeter, it's 10 to the 4. So 400 into 10 to the 4. So that is NCR. So if you calculate that one, pi squared so pi squared into 10 to the 9 into 400 into 10 to the 4 so, and then you divide that by 9,000. So you might get a value for NCR. Okay, so you'll get a value for NCR. So that value is going to tell you how much load this member can carry. So let's work out and tell me the value for NCR. In the meantime, I'll check my calculator for the value. So pi squared that is 9.748 into 10 to the 10. Okay, so here 200 into 10 to the 9, so that's 200 gigapascal. So that is, there's a little mistake here, 200 gigapascal. That is 200 into 10 to the 9 Pascal. So Pascal is Newton per meter squared. So then I have to divide this by another 10 to the 6. So another 10 to the 6 will go on this. So that is 9 into 748 into 10 to the 4 Newton. So how many kilonewton? This one is 400 into 10 to the 4 millimeter squared. So this one is 200 into 10 to the 3, that is 200,000 Newton millimeter squared. Then this 9,000 squared. Okay, so pi squared into 200,000 into 400 into 10 to the 4, then divide by, so that is becoming it's 10 to the 3. That is 97.478 kilonewton. So 97.478 kilonewton. That is the value for the NCR. So when you have NCR 97.478, you can get lambda bar. So the lambda bar is A into F5. So that is 2,920. 2,920 into Fy is 355 divided by 97,478. So that is square root of 20 into 97. So that is square root of 2,920 once again 355 divided by 97,478. 3.26. So lambda bar is 3.261. So we got the lambda bar 3.261, and for the buckling curve we can choose and the how to choose the buckling curve is, say our section, the hot section is hot roll section, and H over B, so H over B is 1, so H over B is less than or equal to 1.2, falling under this category with TF less than 100 millimeter. Okay, so H over B because it's column, and for the UKC it's 152 by 152, so it is less than 1.2. So for this category, if you take buckling, this YY axis is a strong axis, ZZ is a weak axis. So we need to choose the buckling about ZZ axis, the weakest axis. Curve is C. The curve is C here. Okay, so the curve is C. So if you take the curve C, so the curve C, and the value is 3.26, the lambda bar. So that maximum is 3, it's 0.1. It's 0.1. So here the table has up to 3, and when we substitute the value, we'll get the actual value. So it's roughly 0.1. So your reduction factor she is factor 0.1. Okay, so 0.1, because for 3 it is 0.1. So our one is 3.26, which is less than 0.1. So the 0.1 means your she value does not satisfy this. Okay, so we have considered the she value should be greater than or equal to 0.964 to satisfy the section. So now the section is going to fail by buckling because it doesn't satisfy this requirement. So it is 0.1. Okay, it's 0.1 means the failure is dominated. So the NBRD is 0.1 into A into Fy over gamma M1. Okay, so 0.1 into 2,920, 355 over 1. So that is how much? 2,920 into so that is 130 3.66. So 103.6 kilonewton is the buckling capacity. So NED greater than NBRD. Hence, the section fails for global buckling resistance. So it fails for the global buckling resistance. Now the section has satisfied the capacity required, but it failed because of this member tend to be very slender, so it has a high probability of buckling at 103.6 kilonewton. So it will never reach that NED of 1000 kilonewton. So therefore we need to choose a bigger section. So although NED equal to NCRD satisfied squashing capacity, the section fails for NED NBRD. Okay, so it is not satisfied. So NBRD is much lower than NED. Therefore, we need to choose a bigger section. So in this process you have to choose a bigger section, and then you redo the whole thing. Anyway, when you choose a bigger section, it will satisfy the squashing capacity. You need to check whether it's falling under class 1, 2, 3, and you have to check for the bending capacity or bending resistance. So this is how you take or you approach a beam problem, a column problem. When you have a column, you have a design action load from the support reactions. So the support reactions of the analysis will provide you the it will provide you the required capacity. Okay, so if the member satisfies both the both the compression capacity as well as global buckling requirement, then the member can be used. So now we have, in this question, we have about 1000 kilonewton load is acting on the column. So that load is derived from the support reactions of the beam, and that support reaction is acting as a load on the column, and that load should be carried by the structure. Okay, so that load should be carried by the structure. So now we need to, if it doesn't satisfy, if NBRD is less than NED, then you have to choose a bigger section. So I would choose a slightly larger section for the next cycle. Say if I take this one, so instead of 152, 123, maybe I can choose something like 254, 254, 73. So in this case, thickness is less than 16, so it is 355. So if you choose this section, the area is high, so it will anyway satisfy NCRD. We have to see whether it can satisfy the uh, in BRD. So regardless of the section, your this value, regardless of the load, this value will be independent because it's depending on pi squared EI and I and L squared. So L squared also independent of the cross section. Only value you get about the cross section is the I value. So now if I choose this section, so if you consider 254, 254, 73. UKC. Okay. Now everything, the lambda bar is going to be different because your A and NCR are going to be different. So NCR pi squared EI over L effective squared. So pi squared, let's leave it is E of this section. So that is 200 3 Newton millimeter squared. I for the 254, 254, 73. If you look at the I section, 254 to 73. Second moment of area by the weaker axis, so that is in this row 3910. So that is 3910 into so the area for this section 3910 is for the I value. So that's 10 into I is given as centimeter to the 4, so that is in 10 to the 4. So that is in 10 to the 2. Over L squared is 9,000 square. So if you look at this NCR now, the NCR is pi squared into 200,000 into 3910 into 10 to the 4 divided by 9,000 square. So that is 952.8 kilonewton. So that is 952.84 kilonewton. Okay, that is NCR. So if you substitute NCR to lambda bar is square root of A into Fi over NCR. So A into Fi is the A is 254, 73, 93.1 centimeters square. So A is 93.1 centimeters squared. So that is A 9,310. Fy is 355 because yeah, steel thickness is less than 16 millimeter for both. So if you take this one, it's 11.1 and 6.48. So that is thickness of the weapon flange is 8.6 and 14.2. So that is still thinner than 16. So 355 remains same, and NCR is 952.84. into 10 to the 2. So that is 3 point, so let's take 93.1, 355. So that is lambda bar is 3.47. That is still higher than the uh, value. It's going to be zero point 0.1. So you need to choose a bigger section and see whether it can satisfy the lambda bar and the she requirement. So she should be around 0.964 if it is in this case, but now our section ends in BRD. Okay, so in BRD, RD is going to be she into A into Fy over gamma M1. So for 3.46, it's going to be roughly 0.1. The curve, say, if you consider this for example, if you consider again TF is less than 100 and the H over B is less than 1.2, so it's going to be curve C for the weak axis. So if it is curve C, if you look at the values that I have, roughly around 3 point something, so it's 0.1, roughly 0.1 approximately. So she is 0.1, but you can get the accurate value of the she as well using the equations that we have seen. So that is 0.1 into A is equal to 93.1 into 10 to the 2, 355. So now we can see whether this satisfies the capacity 0.1 into 93.1 into. So now the value is becoming 330.51 kilonewton in BR. So it's still less than 1000. So we need to choose a much bigger section that can satisfy this requirement. So this is going to be an iterative procedure if you have these both possibilities of buckling as well as squashing failure. So if you take a compression member, there are possibly 3 failures. One is squashing, second one is local buckling, third one is global buckling. From your analysis, you can obtain the bending moment, shear force and support reactions. Once you get the support reactions, those support reactions are of some force acting on columns due to the beams. So those support reactions are going to be your axial forces for the columns. Those are NED. So if you take a column for an NED value, then you have to choose the appropriate section. When you're choosing appropriate section, you need to consider the three different failure modes. So a failure could occur in a column due to failure of the material. So that is called squashing. There's no buckling, just the failure of the material. So it's get crushed. Second is local buckling. So local buckling, we can see whether it is class 1, 2, 3 or 4. So based on the classification, we can see whether there will be a local buckling before it reaches the yield stress. So in this case, the yield stress, before it reaches the yield stress in class 1, 2, 3, you will not have a local buckling. So as long as they fall under class 1, 2, 3, we are fine, because we will never let it reach the yield stress. Then the third option is global buckling. The global buckling is done in a similar way that we did. So that is NBRD. So you have to determine this factor Xi, the reduction factor, and that reduction factor Xi can tell us whether this will buckle before actual failure or actual failure will occur. Okay, so those things we can see from these two calculations. So in any member which is under compression and not restrained, so for example, if the column is supported by walls either side, in all four sides, it will not have any such failures because there won't be any buckling. But if it is free to buckle, so that is why LE means effective length. So LE indicate that the effective length means there are only supports at 9-meter interval. So now we need to choose a bigger section that can withstand the load. So you can see that earlier section could only carry 103 kilonewton. Now the next section we have chosen able to carry 330 kilonewton. If we choose another bigger section, it will go up to 1000. So if it exceeds 1000, then that is the section we need to use for this column. Okay, so with that learning, so we have so far we have studied how to design a tensile members, how to design a compression members, how to approach bending elements. So I think other than the lateral torsional buckling, we have seen all other different types of failure modes that you can anticipate in a steel element or steel structure. So you can utilize this learning to complete your assignment, because the next step, once you complete the beam design, the next step is column design. For the column design, you need to know these design techniques. So now we'll stop now, and we'll continue Wednesday again with the lateral torsional buckling, which is similar to this global buckling of columns. So I'll see you again with the lecture on Thursday, and I can meet you during the design classes. Thank you.